A perfect hexagon spins at Saturn's north pole. This is not a computer graphic or an artist's concept, but a real, persistent storm wider than our entire planet. A geometric shape etched into the clouds of a gas giant. Saturn, famous for its dazzling rings, hides one of the solar system's most bizarre and enduring mysteries right above its north pole. By the end of this, you will understand the forces that can carve a six-sided wonder into the atmosphere of a world. We will explore how a storm could last for decades, why it has exactly 6 sides, and what this tells us about the hidden heart of Saturn itself. What does such perfect geometry in a place of chaos make you wonder about the universe? The first hints of this anomaly arrived not with a bang but a blur. In the early 1980s, as the twin Voyager spacecraft raced past Saturn on their grand tour of the outer solar system, their cameras captured something utterly unexpected at the planet's north pole. The data was grainy, the light was poor, but there it was, a faint, 6-sided pattern in the clouds. For the scientists staring at those first images, it defied every expectation. Planetary atmospheres are realms of swirling chaos, of eddies and bands and storms that come and go. They do not produce perfect, persistent polygons. The initial reaction was a mixture of disbelief and intense curiosity. Could it be an artifact of the imaging process, a trick of the light and shadow? But as the data was cleaned and analyzed, the shape held. A geometric storm, a hexagon nearly 25,000 kilometers across, was spinning at the top of Saturn. It was a puzzle without a precedent, a mystery that would have to wait decades for a closer look. That closer look arrived with the Cassini spacecraft, which entered orbit around Saturn in 2004. Unlike the fleeting Voyager flybys, Cassini was a long-term resident. It watched Saturn through seasons, its instruments trained on the North Pole as the long winter darkness slowly gave way to spring sunlight. What Cassini revealed was breathtaking. The hexagon was not just real, it was a towering, deeply rooted atmospheric structure. It was a jet stream, a river of wind screaming along at over 300 kilometers per hour, tracing that impossible 6-sided path. The clarity of the images allowed teams of scientists, like those led by researchers at the University of Oxford and NASA, a jet propulsion laboratory, to study its behavior in detail. They watched smaller storms, like cars in a cosmic traffic jam, get caught in the flow and whip around the hexagonal track. They measured its stunning stability, realizing this wasn't a fleeting weather pattern. It was a permanent feature of the planet, a piece of atmospheric architecture that had likely been spinning for decades, if not centuries. Cassini transformed the hexagon from a blurry curiosity into a profound enigma, a question written in cloud and wind that demanded an answer. The sheer size of this structure is almost impossible to comprehend with our earth-bound senses. Picture a wall of cloud, a sheer cliff of swirling atmosphere, tracing a perfect 6-sided path. That is Saturn's hexagon. It is a jet stream, a river of wind so fast and so stable it has carved a geometric shape into the sky. Now try to hold its scale in your mind. Each one of the hexagon's 6 sides is longer than the entire diameter of our planet. You could line Earth up against one of those walls and our whole world would look small. In fact, the entire hexagonal area, the space enclosed by those rushing winds, is so vast that nearly 4 Earths could fit inside it comfortably. This isn't just a storm, it's a continent of weather, a permanent geographic feature made of nothing but air and time. From above, the view is both beautiful and strange. The hexagon itself often glows in hues of gold and pale yellow, colors painted by complex chemical reactions in Saturn's upper atmosphere. Sunlight interacts with methane and other compounds, creating that perpetual, hazy sunset. And at the very center, locked in the eye of this geometric hurricane, often spins a deep, calm blue vortex. It's like a silent, dark pool at the heart of a golden maze. Remember, you are not looking at a solid surface. Saturn has no ground to stand on. This entire spectacle exists tens of kilometers above the planet's deeper layers of liquid metallic hydrogen, a high-altitude pattern etched into the clouds, a drawing made by the wind itself on a canvas the size of worlds. Locked within that golden maze is a storm within a storm. At the very center of the hexagon, pinned in place by the surrounding jet stream, spins a colossal vortex. It is a hurricane, but one of alien proportions. If you were to fly over it, you would see a deep, dark blue eye, often hundreds of kilometers across, surrounded by its own bands of swirling cloud. The winds within this central maelstrom are even more ferocious than the hexagon's own jet stream, whipping around at speeds that dwarf anything we know on Earth. To put that in perspective, a Category 5 hurricane on our planet might have sustained winds of around 250 kilometers per hour. The vortex at Saturn's heart can reach nearly 500. It is a perpetual engine of chaos, yet it is perfectly contained, held in a stable orbit by the unyielding geometric walls of the hexagon around it. This central vortex is not a static plug, however. It is a dynamic, churning heart. Scientists watching with Cassini's instruments witnessed smaller, fleeting storms, brief, intense swirls of cloud spinning off from the edges of the main vortex and dancing chaotically inside the hexagonal arena before being reabsorbed or fading away. These transient whirlwinds are like sparks thrown from a grinding wheel, hints of the tremendous energy being circulated and dissipated within the system. Studying this central vortex is crucial because it acts like a control knob for the entire hexagon. The energy from the deeper, warmer layers of Saturn rises and fuels this central storm. The vortex then interacts with the faster-moving hexagonal jet stream that encircles it, creating a complex dance of energy transfer. By measuring the temperatures, wind speeds, and chemistry within the vortex, researchers can trace how heat from Saturn's interior is converted into the kinetic fury of the winds, and how that energy is then distributed along the six-sided track to maintain its impossible shape. The vortex is not just a spectacle, it is the power source for the entire geometric wonder. The key to this geometric marvel lies not in solid ground, but in the physics of moving air. The hexagon is at its heart a jet stream. On Earth, our jet streams are wavy, meandering rivers of fast wind that snake across the globe, guiding weather systems and shifting with the seasons. They are fluid and chaotic, bending around mountain ranges and responding to temperature differences between the equator and the poles. Saturn's hexagonal jet stream is the opposite. It is a river of wind of almost unbelievable stability, tracing the same six-sided path for decades without wavering. This difference points us toward the alien nature of Saturn itself. To understand how a shape forms in such a fluid environment, we need to think about wind shear. Imagine two layers of air moving past each other at different speeds. The boundary between them is a zone of shear, a place of friction and instability that can generate swirling vortices, like eddies forming where a fast river meets a still bank. On Saturn, the hexagon appears to mark the boundary between two such immense atmospheric bands. Inside the hexagon, the air rotates at one speed, outside it another. The sharp velocity gradient at this boundary is the energy source, the raw power that sustains the phenomenon. So why a hexagon and not a circle or a wavy line? The leading theory among planetary scientists is that we are looking at a standing wave. Think of it like the pattern you can create by vibrating a plate of sand. At certain frequencies, the sand organizes itself into precise geometric shapes like stars or hexagons. The vibrating plate provides the energy, and the properties of the sand dictate the shape that emerges. Saturn's atmosphere may be doing something similar on a planetary scale. The planet's rapid rotation, a day on Saturn is only about 10.5 hours long, provides a powerful organizing force, channeling the chaotic energy of the wind shear into a stable pattern. Mathematical models suggest that under the specific conditions of Saturn's north pole, with its particular wind speeds and rotational forces, the most stable pattern that can form is a six-sided wave. It is not a solid structure but a persistent ripple in the atmospheric fabric, a place where rising and sinking air combined with the planet's spin lock into a resonant geometric dance. The hexagon is essentially a permanent stamp in the clouds, created by the planet's own rotation and internal heat acting on its deep atmosphere. This transforms the mystery from a question of what it is to a deeper puzzle of planetary machinery. That rapid rotation is the master sculptor of Saturn's atmosphere. A day on Saturn is a blur, just 10.7 hours from one sunrise to the next. This dizzying spin does more than mark time. It physically reshapes the planet, squeezing it so that its poles are noticeably flattened and its equator bulges outward. More importantly for our hexagon, this spin is the fundamental force that organizes the chaos. On Earth, our weather systems bump against mountains and scrape across continents, their energy dissipated by friction with the solid ground. Saturn has no such breaks. It is a world of pure fluid dynamics, a deep, churning ocean of gas thousands of kilometers thick with nothing solid to interrupt the flow. This lack of friction, combined with the immense rotational energy, allows atmospheric patterns to grow to staggering sizes and achieve a stability impossible on our own world. Storms here are not fleeting events measured in days, but permanent fixtures that can last for centuries, becoming embedded features of the planetary climate. This is the canvas upon which the hexagon is drawn. The primary tool for this organization is the Coriolis effect. It is the same force that causes hurricanes on Earth to spin in a particular direction. As air moves across a rotating planet, its path is deflected, curving to the right in the northern hemisphere and to the left in the southern. On a rapidly spinning world like Saturn, the Coriolis effect is exceptionally powerful. It acts like an invisible hand, constantly shepherding parcels of air, forcing any large-scale movement into a rotational pattern. It is this intense Coriolis influence that helps confine the raging winds into a coherent jet stream, and under the specific conditions at the pole, locks that stream into a resonant standing wave with six sides. The hexagon, therefore, is not a random shape, but a direct mathematical consequence of Saturn's spin acting upon its deep, fluid atmosphere. It is the planet's own rotation, written in cloud and wind, a signature of its fundamental nature. But how do we know this theory of a planetary standing wave holds any water, or in this case, any gas? The answer comes from turning our planet into a laboratory for Saturn's sky. Here on Earth, scientists have built scaled-down versions of this alien weather system, not with clouds and ammonia, but with simple water and spinning tanks. These experiments are masterpieces of fluid dynamics, designed to strip away the complexity of a gas giant and reveal the fundamental physics at its core. In a typical setup, a cylindrical tank is filled with water representing Saturn's deep atmosphere. The tank is placed on a rotating table, spinning to simulate the planet's rapid rotation. At the center, a small, rotating disk often acts as the central vortex, the storm at the hexagon's heart. By carefully controlling the speed of the tank and the inner disk, researchers can watch the fluid between them organize itself. And something remarkable happens when the conditions are just right, when the rotation is fast enough and the shear between the inner and outer flows is strong enough. The chaotic fluid doesn't form a simple circle. It breaks into a stable geometric polygon. Triangles, squares, and yes, perfect hexagons emerge in the swirling water, tracing their sharp-edged paths as clearly as if they were drawn with a ruler. These are not artistic interpretations, they are direct physical recreations of the principle at work. The viscosity of the water, its thickness, and the precise rotational speeds determine the number of sides. By tweaking these parameters, scientists can essentially dial in different polygons, proving that under the right mix of forces, nature prefers geometric order over formless chaos. This laboratory work is the crucial bridge between abstract theory and cosmic reality. It provides a tangible, testable model that says, yes, the physics we understand here on Earth can indeed create a Saturn-like hexagon under controlled conditions. These spinning tanks act as a proving ground, allowing researchers to isolate variables and observe cause and effect in a way that's impossible while staring at a distant planet. The success of these experiments gives tremendous confidence to the more complex, three-dimensional computer models that simulate Saturn's entire atmosphere. They tell us we are on the right track, that the forces shaping a whirlpool in a bucket are the same fundamental forces carving a continent-sized storm on a world a billion kilometers away. These spinning water tanks provide a beautiful proof of concept, but Saturn's reality is far more complex. To truly unravel the hexagon, we must move from the physical lab to the digital realm, where supercomputers construct entire virtual planets. Here, scientists don't just recreate a single effect, they build a complete, breathing simulation of Saturn's atmosphere, layer by turbulent layer. They feed in every scrap of data. We have the staggering wind speeds from Cassini, the temperature gradients measured by infrared sensors, the density of the cloud decks, and the relentless 10.7-hour rotation. Then they press start and watch what emerges from the chaos of billions of calculated interactions. The goal is breathtakingly simple yet profoundly difficult: to see if, given the right ingredients and the known laws of physics, a stable hexagon simply forms on its own. And in recent years, these simulations have achieved something remarkable. Teams at institutions like the University of Oxford and the Massachusetts Institute of Technology have run models that, after the virtual equivalent of years spinning in their digital space, spontaneously generate a persistent, six-sided jet stream at the North Pole. It is not forced into the code, it emerges from it, a testament to the power of the underlying physics. These breakthroughs are more than just a match for a pretty picture. They allow researchers to play God with a gas giant. They can tweak variables in ways impossible in reality. What happens if we slow Saturn's rotation by just a few percent? The hexagon vanishes, replaced by chaotic bands. What if we change the depth of the jet stream or the temperature difference between the pole and the surrounding atmosphere? The model shows the shape becoming unstable, wobbling and dissolving. Through millions of these virtual experiments, the simulations identify the precise, narrow window of conditions required for the hexagon's longevity, a delicate balance of rotational force, wind shear, and atmospheric depth that Saturn, by some cosmic accident, happens to perfectly meet. This makes computer modeling our most powerful telescope into the storm's heart. It is the only tool that lets us test hypotheses about the flow of energy from the deep interior, or visualize how smaller eddies get swept up and reinforce the larger pattern. By watching the hexagon live and breathe in silicon, we gain confidence that we are not just describing a mystery, but beginning to understand the machinery that makes it tick. The hexagon is not a frozen painting on Saturn's sky, but a living, breathing weather system. For over 13 years, the Cassini spacecraft kept watch, observing nearly half of a Saturnian year as the planet's north pole slowly emerged from a decades-long winter. This extraordinary timeline gave scientists a front-row seat to a seasonal transformation on an alien world. For years, the hexagon and its central vortex were shrouded in the deep blue shadow of polar night, a dark arena visible only in the faint glow of starlight and Saturn's own thermal radiation. Then, as spring arrived and sunlight finally crept over the pole, a remarkable change began. The deep blue vortex at the center started to fade, its colors shifting through hues of teal and eventually to a rich golden yellow, matching the haze of the surrounding hexagon walls. This was not just a trick of the light, it was chemistry in action. The intense ultraviolet light from the sun was acting like a cosmic paintbrush, driving photochemical reactions in the high atmosphere. It was breaking apart methane molecules and creating new, more complex hydrocarbons that formed a thick, golden haze. The storm was literally changing color with the seasons, revealing itself as a system intimately connected to the amount of solar energy it received. This transformation proved the hexagon is not a shallow pattern etched on the cloud tops, but a deep-rooted structure. The seasonal changes in sunlight penetrate hundreds of kilometers down, influencing temperature and wind patterns. The fact that the hexagon maintained its precise geometric shape throughout this monumental shift from the cold, dark stability of winter into the warming turbulence of spring is a testament to its incredible stability. It adapted without breaking form, a six-sided engine that modulates its internal chemistry and energy flow across seasons that last longer than a human generation. Watching this time lapse of a world is a humbling reminder of the scales at which other planets live, where a single storm can outlast civilizations and change its face with the slow turn of a cosmic clock. Yet this six-sided wonder does not exist in isolation. To truly grasp its strangeness, we must see it alongside its celestial neighbors. Our own planet Earth has a polar vortex, a term you might hear in winter weather forecasts. But Earth's version is a vast, meandering circulation of cold air high in the stratosphere, a loose and shifting zone that influences jet streams and can push frigid air southward. It is not a sharply defined structure you could see from space, and its shape and strength change with the seasons, sometimes even splitting into two lobes. It is a fluid part of our dynamic weather, not a permanent geometric fixture. Then we have Jupiter, Saturn's colossal sibling. The Juno spacecraft recently revealed that Jupiter's poles are utterly alien landscapes, but in a different way. Each pole is crowned not by a single polygon, but by a swirling gallery of giant cyclones. At the North Pole, 8 of these massive storms encircle a central one like petals on a nightmarish flower. At the South Pole, 5 cyclones perform a similar dance. These are stable, long-lived arrangements, but they are distinct, swirling storms held in a geometric arrangement by mutual repulsion, not a single continuous wall of wind. This makes Saturn's hexagon the solar system's true outlier. It is not a collection of storms, but one unified structure. It is not a loose circulation, but a razor-sharp jet stream tracing a perfect geometric path. Its stability is measured not in years but in generations. While Jupiter's polar cyclones are a stunning example of organized chaos, Saturn's hexagon is something else entirely, a piece of pure atmospheric geometry. This comparison throws its uniqueness into stark relief. In a solar system filled with whirlwinds and vortices, only Saturn has managed to inscribe a persistent, perfect polygon into its sky. A six-sided signature that remains one of the most precise and enduring natural formations we have ever witnessed. 40 years is a long time for a storm. On our planet, the most powerful hurricanes rage for a week, maybe 2, before they run out of warm ocean water and crumble against continents. Saturn's hexagon has been spinning, unchanging, for at least that long, since the Voyager probes first glimpsed it. The real wonder is that it might be centuries old, a permanent fixture in an alien sky. This staggering longevity is perhaps its deepest mystery. How does a storm not just form, but lock itself in place for generations? The answer begins with what Saturn lacks: a solid surface. Earth's weather is constantly bumping into things: mountains that disrupt airflow, continents that create temperature extremes, and vast oceans that act as both fuel sources and heat sinks. This complex terrain creates our dynamic, ever-changing weather, but it also acts as a brake. Friction with the ground saps energy from storms, causing them to dissipate. Saturn is a world of pure atmosphere, a bottomless ocean of hydrogen and helium over 10 times wider than Earth. A storm here has nothing to scrape against. Once a pattern like the hexagon establishes itself in that deep, churning fluid, there is no continental landmass to break it apart. it can simply spin, a self-contained weather system in a frictionless arena, potentially for as long as the energy feeding it remains constant. And that is the second key, the constant energy input. Our hurricanes are heat engines powered by the sun-warmed tropical oceans. When they move over land or cooler water, the fuel supply is cut and they die. Saturn's hexagon draws its power from a far more reliable source, the planet's own internal furnace. Deep within Saturn, leftover heat from its formation over 4 billion years ago, combined with the slow sinking of heavier helium through lighter hydrogen, generates tremendous warmth. This heat steadily rises from the interior, driving convection, the same process that makes water bubble in a boiling pot. On a planetary scale, this rising heat creates colossal updrafts and downdrafts, stirring the atmosphere and generating the immense wind shear that fuels the jet streams. The hexagon is essentially plugged directly into the planet's core. It is not a temporary weather event, but a permanent release valve for Saturn's internal energy, a visible signature of the churning chaos far below the cloud. This leads scientists to a profound possibility that the hexagon is not a surface feature at all, but the tip of a deep-rooted atmospheric structure. Some models suggest the jet stream forming its walls may extend thousands of kilometers down into the planet's interior, anchored in the differential rotation of Saturn's deeper layers. If this is true, the hexagon we see is just the surface expression of a planetary scale process, a six-sided chimney funneling heat from the depths. That kind of deep foundation would grant it a stability beyond any earthly storm, making it as much a part of Saturn as its rings. So is it permanent in a human time frame? It certainly appears to be. It has persisted through seasonal changes and solar cycles. Whether it has existed for 1,000 years or will last for 10,000 more is a question we cannot yet answer. But its endurance forces us to rethink what a storm can be, not a fleeting disturbance, but a fundamental piece of a planet's anatomy, a geometric heartbeat pulsing in time with the slow release of a world's inner fire. That enduring stability forces a critical question: how deep does this geometric storm truly go? Is it a spectacular but shallow pattern painted on Saturn's cloud tops, or is it a signpost pointing to the very heart of the planet? This is the central debate among planetary scientists today, and the answer reshapes our entire understanding of gas giants. On one side is the shallow weather layer theory. This view suggests the hexagon is a magnificent surface phenomenon, a standing wave confined to the upper few hundred kilometers of Saturn's atmosphere. Think of it like a pattern on the surface of a very deep, very fast-moving river. The energy comes from wind shear between different cloud bands, and the planet's rapid rotation organizes that energy into the six-sided shape we see. The evidence for this is compelling in its simplicity. Cassini's cameras and spectrometers observed the hexagon changing color with the seasons, a process driven by sunlight interacting with high-altitude chemicals. This strongly implies the structure we see is intimately connected to the upper atmospheric layers where sunlight can penetrate and cause these reactions. Furthermore, sophisticated computer models have successfully generated stable hexagons by simulating only the upper atmospheric dynamics, without needing to invoke any deep planetary roots. It suggests the machinery for this wonder might all be right there in the cloud decks we can see. The opposing view, however, is far more profound. The deep structure hypothesis proposes that the hexagon is just the visible tip of a planetary scale iceberg. In this scenario, the jet stream forming its walls is not a surface feature, but a column of fast-moving wind that extends thousands of kilometers down into Saturn's churning interior. It could be anchored in the differential rotation of the planet's deeper layers, where hydrogen transitions from a gas to a liquid metal. The hexagon, then, would be a chimney, a geometric conduit for transporting heat and momentum from the deep interior up to the cloud tops. Evidence for this comes from the storm's mind-boggling stability and power. A shallow weather pattern might be expected to wobble, to shift, or to dissipate over 40 years, especially as seasons change. The hexagon's razor-sharp persistence suggests it is being constantly and powerfully reinforced from below. Some measurements of wind speeds at different altitudes, though difficult to obtain, hint at a coherence that goes deeper than just the cloud tops. If the deep theory is correct, then the hexagon is not merely a storm, it is a window. By studying its 6 sides, we are indirectly measuring the chaotic convection and complex fluid dynamics happening in a place we can never see, the hidden heart of a gas giant. This transforms it from a meteorological curiosity into a vital diagnostic tool for planetary science. So why does this academic debate matter so much? It is because the depth of the hexagon tells us what kind of planet Saturn really is. If the storm is shallow, it means Saturn's weather layer is astonishingly complex and self-organizing, capable of creating and maintaining precise geometric order over immense scales and times. It would be a testament to the power of rotation and shear in a deep atmosphere. But if the hexagon's roots are deep, it reveals something even more fundamental, that the interior of a gas giant is not a uniform, featureless fluid. It suggests the existence of stable, structured columns of motion that penetrate through thousands of kilometers, linking the interior's heat engine directly to the patterns in the sky. This would mean the atmospheres of giant planets are not separate from their insides, they are a continuous, dynamic whole. The hexagon becomes a kind of planetary fingerprint, a unique pattern emerging from the specific way Saturn churns and spins. Solving this mystery requires looking past the beautiful shape itself to the subtle tremors and vibrations it might be causing in the space around it. There is a sound to Saturn we cannot hear. Deep within its churning interior, vast acoustic waves are constantly ringing out, traveling through the dense fluid like the deep tones of a planetary bell. This leads us to one of the most compelling and exotic explanations for the hexagon, the theory of planetary resonance. Think of it not as a storm, but as a note held in the atmosphere, a standing wave of unimaginable scale. To understand this, picture a drumhead. When you strike it, the skin vibrates not randomly, but in specific, stable patterns called modes. Depending on where and how you strike, you might see a circular pattern, or a pattern with nodes that look like stars or polygons. The drumhead vibrates as a whole, and the shape you see is the result of the entire structure resonating at a specific frequency. Now, imagine Saturn itself as a colossal, fluid sphere. The heat churning in its core, the sloshing of its deep layers of metallic hydrogen, all of this generates immense pressure waves, essentially sound waves of very low frequency. These waves travel upward through the planet, at certain resonant frequencies specific to Saturn's exact size, composition, and rotation. These waves can reinforce each other, creating a stable, repeating interference pattern. Like the vibrating drumhead, the entire planet can ring in a specific mode. The hexagon we see at the cloud tops, according to this theory, is simply the surface manifestation of that deep, resonant vibration. It is the crest of a planetary scale wave, frozen in place by the perfect synchronization of Saturn's internal acoustics. This transforms the hexagon from a weather pattern into a direct sonic signature of the planet's hidden heart. It becomes a visible echo of the turmoil far below, a six-sided ripple on the surface of a world that is, in a very real sense, constantly singing to itself. The resonance theory offers a beautifully unified explanation. It directly connects the shape's geometric perfection to the global properties of Saturn itself. The number of sides is not arbitrary. It is dictated by the mathematics of the resonant mode, much like the length of a guitar string dictates the note it plays. This also elegantly explains the hexagon's staggering stability. A resonance, once established, is self-reinforcing and incredibly difficult to disrupt. Energy from the interior continuously feeds the wave, locking it into place against the forces that would normally tear a storm apart. It suggests we are not looking at a local atmospheric accident, but at a fundamental vibrational state of the entire planet, a note that has been held for perhaps thousands of years. This idea pushes our understanding to its limits, forcing us to see Saturn not just as a ball of gas, but as a complex, resonant cavity where the music of its formation still echoes in the clouds. Saturn's six-sided signature may not be a solitary masterpiece. If its geometry is born from fundamental physics, then the universe could be filled with similar wonders, hidden in the swirling atmospheres of distant worlds. The key lies in the recipe revealed by our experiments and models, a rapidly rotating fluid body with deep layers and powerful internal heat. Any planet or even a failed star that meets these conditions could, in theory, etch polygons into its sky. Take Jupiter, for instance. Its poles are crowned with geometric arrangements of cyclones, but not a single, continuous hexagon. This difference is likely a matter of specifics, the precise depth of its jet streams, the strength of its internal heat flow, or the viscosity of its atmospheric layers. Jupiter's conditions favor a bouquet of storms, while Saturn's tune a solitary, resonant note. What about Uranus, tipped on its side with an extreme seasonal cycle? Or Neptune, where the fastest winds in the solar system scream? Their different rotations and internal structures might generate other shapes, perhaps pentagons or octagons, if the delicate balance for a standing wave is struck. The possibility extends far beyond our solar system. Brown dwarfs, those enigmatic objects straddling the line between planet and star, are known for their turbulent, cloud-filled atmospheres and rapid rotation. They are prime candidates for polygonal weather, and among the thousands of exoplanets we have discovered, many are hot Jupiters, gas giants orbiting perilously close to their stars. These worlds are likely tidally locked, with one face in perpetual blistering day and the other in endless night. This creates temperature extremes that could drive ferocious jet streams, and their rapid rotation might sculpt those winds into stable, geometric patterns we can only imagine. We have not yet seen another hexagon, but that is a limitation of our vision, not necessarily of nature. Our telescopes cannot yet resolve the cloud tops of distant gas giants in enough detail to spot a six-sided storm. Yet the physics tells a compelling story that Saturn's hexagon is not a fluke, but a demonstration of a universal principle. This transforms the mystery from a singular anomaly into a potential class of atmospheric phenomena, a hidden gallery of geometric storms waiting in the dark. The search for them becomes a new way to listen to the music of other worlds, to decode the resonant frequencies of spinning giants across the galaxy. Perfect geometry in a place of chaos feels like a message. It is no surprise, then, that Saturn's hexagon has escaped the pages of scientific journals to spark the wider public imagination. Its stark, unnatural shape makes it a star of space documentaries, where it is often presented as one of the solar system's great unsolved puzzles, a visual hook that immediately grabs viewers and pulls them into the story of planetary exploration. In science fiction, art, and literature, the hexagon is frequently reimagined as something far more than a storm. It becomes an alien megastructure, a vast energy grid constructed by an ancient civilization, or a stable wormhole portal to another dimension. Its precise angles seem engineered, not born from wind and gas, making it a perfect canvas for speculative wonder. This leap from atmospheric phenomenon to alien artifact is fueled by a very human instinct to see design in the deeply unfamiliar. When nature produces something that looks so deliberately crafted, it challenges our assumptions about what is possible without intelligence. This has inevitably spiraled into online conspiracy theories that claim the hexagon is proof of hidden activity on Saturn, a secret base or a dimensional gateway kept from the public. While these ideas lack any scientific basis, their persistence is a backhanded compliment to the hexagon's power. It is so bizarre that some find it easier to believe it is artificial than to accept it as a natural, if utterly extraordinary, weather pattern. This cultural journey from day to point to myth highlights a crucial function of such mysteries. The hexagon's strange beauty acts as a gravitational force, pulling in people who might never read a paper on fluid dynamics. It asks a question simple enough for anyone to understand. Why is it a hexagon? That question is a gateway. It leads the curious from a striking image to the underlying science, to the concepts of jet streams, planetary rotation, and resonant waves. In this way, the storm is more than a subject of study. It is a phenomenal tool for public engagement. It demonstrates that planetary science is not a dry catalogue of facts, but a living detective story filled with awe-inspiring phenomena that defy easy explanation. The hexagon reminds us that the universe is capable of wonders that look like magic, and that the process of unraveling them, of replacing mystery with understanding, is one of humanity's most thrilling adventures. But every mission, no matter how brilliant, must one day end. For Cassini, that end was engineered to be as spectacular and scientifically valuable as its entire 13-year tour. Mission planners designed a final act of breathtaking audacity, a series of 22 orbits they called the grand finale. In these last months, Cassini did something no spacecraft had ever dared. It repeatedly dove through the narrow, unexplored gap between Saturn and the innermost edge of its rings. This was a region of space only about 2,000 kilometers wide, a cosmic tightrope walk where a single collision with a ring particle could have been catastrophic. The spacecraft made these perilous plunges, gathering data until its final breath. During these final dives, Cassini's instruments were trained not on the rings or the moons, but directly on Saturn itself. Its radio antenna measured tiny fluctuations in the planet's gravity field as the spacecraft was tugged by the mass distribution inside Saturn. Its magnetometer mapped the internal magnetic field with exquisite precision. These were not pictures of clouds, they were X-rays of the planet's soul. The data revealed a planet with a more complex and fuzzy internal structure than previously thought. A world where the core is not a distinct, solid ball, but a diffuse, blended region of ice, rock, and metallic hydrogen that may extend across a staggering 60% of the planet's radius. This revelation is crucial for the hexagon mystery. A large, fuzzy core means the interior's rotation, which generates the magnetic field, is more complex and may interact with the overlying fluid layers in intricate ways. The deep-rooted theory of the hexagon hinges on understanding how motions in the interior couple to the weather layer above. Cassini's final, direct measurements of gravity and magnetism are the key to unlocking that connection. Scientists are still, years later, mining this final dataset, using it to build ever more accurate models of Saturn's churning heart. Every new insight into the planet's interior rotation, the depth of its jet streams, and the source of its internal heat directly informs the debate over whether the hexagon is a shallow wave or a deep planetary resonance. Cassini's last gift was to give us the tools to listen to Saturn's deepest vibrations, the very frequencies that might be singing the hexagon into existence. We owe our intimate knowledge of this six-sided storm entirely to that lone robotic explorer. It transformed the hexagon from a grainy, puzzling shape in Voyager's old photos into a dynamic, living system we watched change with the seasons. It gave us the close-ups, the wind measurements, the chemical maps, and the long-term observations that turned a mystery into a solvable puzzle. Cassini is gone, vaporized in Saturn's atmosphere to protect the pristine moons it discovered, but its legacy is a library of data that will fuel discoveries for decades to come. The hexagon remains, spinning silently, waiting for the next generation of scientists armed with Cassini's final transmissions to finally decipher its six-sided song. Cassini's data left us with a map, but the territory itself remains shrouded in mystery. The hexagon's very perfection raises questions that still echo in labs and journals today. First, and most famously, why exactly six sides? Our models show that a fast-rotating fluid can settle into polygonal shapes, but the specific number depends on delicate balances of wind speed, viscosity, and planetary rotation. The fact that Saturn's conditions produce a hexagon and not a pentagon or an octagon is a precise fingerprint of its atmospheric recipe. Tweaking a variable in a simulation by just a few percent can change the polygon's shape, so the enduring hexagon tells us Saturn's north pole exists in a remarkably stable and narrow band of physical conditions. But we still do not know the exact formula that nature is using. This leads directly to the second puzzle: what determines its colossal size? Each side stretches over 13,000 kilometers. Why is the hexagon 25,000 kilometers across and not 10,000 or 50,000? The size is likely tied to the depth and strength of the jet stream forming its walls, and perhaps to the latitude where certain atmospheric waves can resonate. It is as if the planet has a preferred frequency for this standing wave, and the distance between its nodes is locked in at this immense scale. We have the shape and the size, but we are still searching for the master tuning fork inside Saturn that sets this specific dimension. Then there is the question of depth, the most heated debate. Does the hexagon have a bottom? Is it a shallow pattern or a planetary chimney? Cassini's gravity and magnetic field data from its final dives are now being scoured with powerful new computer algorithms, looking for subtle signatures that might reveal how deep the jet stream's roots penetrate. Scientists are applying techniques from terrestrial weather prediction and oceanography to Saturn's data, trying to trace the flow of energy vertically. The answer will redefine what we know about how gas giants work, whether their dazzling cloud tops are just a thin veneer over a much more organized interior. All of this circles back to Saturn's internal heat, the engine room of the planet. How does the hexagon interact with that mysterious power source? Is it simply dissipating heat from below, or is it actively shaping how that heat is released? Some theories suggest the hexagon's structure might help trap heat at the pole, influencing global circulation in ways we have not yet imagined. Untangling this relationship is like trying to understand a car engine by only looking at the pattern of exhaust smoke. This is why the research is far from over. Across the world, teams are conducting a digital autopsy of the Cassini mission, applying machine learning to find patterns in the mountains of data that human eyes might have missed. They are searching for connections between tiny fluctuations in the hexagon's winds and deeper internal processes, and they are looking to the future. While no mission to Saturn is currently on the launch pad, concepts are being drawn up for orbiters that could carry more advanced radars and atmospheric probes, instruments designed specifically to answer these depth and structure questions. The hexagon, therefore, is not a closed case. It is an active frontier. Every new analysis, every improved simulation peels back another layer, revealing not just answers but richer, more complex questions. It stands as a brilliant reminder that some of science's greatest journeys begin not with a solution, but with a shape in the clouds that refuses to be easily explained. The ultimate answers to Saturn's six-sided storm may require us to go back. While Cassini's legacy is a treasure trove of data, some questions can only be resolved by new eyes, ears, and hands at the planet itself. The next chapter of exploration is already being sketched out in mission concept studies and engineering labs, focusing on tools designed to probe the very mysteries Cassini identified. Imagine an orbiter, but not just a camera platform. Future missions envision spacecraft carrying advanced radar sounders and microwave radiometers, instruments that can peer through Saturn's thick cloud decks like a doctor using an ultrasound. These tools could map the three-dimensional structure of the atmosphere in unprecedented detail, tracing the jet streams that form the hexagon's walls downward for thousands of kilometers to see if they truly have deep roots. Even more ambitious are concepts for atmospheric probes, perhaps even drones or balloons designed to survive entry and float within the alien skies. A probe descending directly into the polar region could measure wind shear, temperature, and composition at different altitudes, providing a vertical profile of the Hexagon's engine room. It could sample the exotic chemistry of the golden haze and the deep blue vortex, telling us exactly what compounds are being cooked up by the storm's unique dynamics. The data would be like having a weather station inside a hurricane, giving us ground truth for all our complex computer models. But to truly listen to Saturn's interior song, we need to think like geologists studying Earth. Scientists have proposed a radical idea, a seismometer for a gas giant. On our world, earthquakes send vibrations through the planet that reveal its internal structure. Saturn has no solid crust, but it does have constant, deep-seated turbulence. A future orbiter equipped with extremely sensitive instruments might detect the subtle pressure waves these internal convulsions create at the cloud tops. By measuring how these waves travel and refract through the planet, we could create a detailed acoustic map of Saturn's interior, pinpointing the boundaries between layers and the churning motions within. This would directly test the resonance theory of the hexagon, searching for the specific vibrational modes that might be sculpting the clouds above. It is a monumental technical challenge, requiring instruments of phenomenal sensitivity, but the payoff would be a revolution in our understanding of giant planet interiors. We would move from inference and modeling to direct measurement. The anticipation for this next chapter is palpable among planetary scientists. Cracking the hexagon's code is not just about solving a single beautiful puzzle, it is about revealing fundamental truth. This storm is a natural laboratory for fluid dynamics operating on a scale and over a time frame we can never replicate on Earth. By finally understanding the precise mix of rotation, wind shear, internal heat, and resonance that creates and sustains it, we unlock a universal principle. The knowledge gained would not only explain Saturn, it would give us a master key for interpreting the swirling atmospheres of every gas giant we see, from Jupiter and Neptune to the dizzying variety of hot Jupiters orbiting distant stars. The hexagon is a Rosetta Stone written in cloud and wind, and we are on the cusp of learning how to read it. The next mission that makes the billion-kilometer journey to Saturn will carry with it the hopes of finally turning this majestic, geometric mystery into profound understanding, a testament to human curiosity reaching across the solar system to decipher the hidden music of another world. Saturn's hexagon is far more than a local curiosity. It is a master key for unlocking the nature of the most common planets in the galaxy. Beyond our solar system, telescopes have confirmed thousands of exoplanets, and the vast majority of those we can characterize are gas giants, worlds of swirling hydrogen and helium with no solid surface. They come in bewildering varieties, from scorching hot Jupiters orbiting close to their stars to frigid, lonely giants drifting in the dark. But they all share a fundamental similarity with Saturn. They are immense spheres of fluid dynamics. When we point our most powerful telescopes at these distant points of light, the data we receive is frustratingly sparse. We might infer a planet's size, its mass, its orbital distance, and with advanced instruments, even hints of the chemicals in its atmosphere. But to transform those faint signals into a true understanding of a world, we need a reference library. We need to know how the physics of a deep, rotating atmosphere actually manifests. This is where Saturn's hexagon becomes invaluable. It is a detailed, up-close case study of how such a planet organizes its chaos. By deciphering the precise mix of rotation, wind shear, and internal heat that carves a stable hexagon into Saturn's clouds, we are essentially learning the grammar of gas giant weather. We can then apply that grammar to interpret the blurrier sentences we receive from light years away. For instance, if we observe an exoplanet with an asymmetric brightness, a hotspot that seems to linger in one place, could that be the signature of a persistent polar vortex like the one inside the hexagon? If our models of atmospheric circulation, refined by Saturn's example, predict that a planet with a certain rotation speed and size should develop stable standing waves, we can search for the subtle, repeating patterns in the starlight filtering through its atmosphere. The hexagon provides the ground truth. The real-world example that proves such long-lived geometric order is not just theoretical, but a natural outcome under the right conditions. This transforms Saturn from a distant neighbor into the closest and most detailed natural laboratory we have for the physics that governs countless worlds across the cosmos. Solving its mystery does not just satisfy our curiosity about one storm. It builds the foundation for understanding an entire class of planets that dominates the galactic population. Every insight into why the hexagon has 6 sides, how deep it goes, and what fuels its endurance directly improves the computer models we use to simulate the climates and evolution of all gas giants. In this way, a spinning hexagon at our solar system's edge becomes a Rosetta Stone for translating the faint whispers of alien atmospheres into a story we can finally understand. The same physics that carves a continent into Saturn's sky is at work in your kitchen. Watch a pot of water as it begins to boil. Just before the rolling bubbles take over, you might see the surface organize into a beautiful honeycomb-like patchwork of cells. Each cell is a hexagon with fluid rising in the center and sinking along the walls. These are Baynard convection cells, a classic demonstration of how a fluid, when heated from below, can self-organize into geometric order. It is a pattern born from instability, from the struggle between the driving force of heat and the smoothing force of viscosity. The hexagons emerge because they are the most efficient way for the system to transfer that energy, packing together without gaps. This is not a coincidence. It is a fundamental principle of fluid dynamics playing out on a scale of centimeters. Now, look at a cliff face made of columnar basalt, like the Giant's Causeway in Ireland. Those towering hexagonal pillars were formed as thick lava cooled and contracted, cracking into a network of polygons. Again, the hexagon appears as the most efficient way to release stress and minimize energy within the solidifying material. Even in the animal kingdom, the compound eyes of many insects are arrays of hexagonal lenses, a perfect tessellation that maximizes light gathering in a limited space. These diverse examples share a deep mathematical thread. They reveal that under certain constraints, whether it's the transfer of heat, the release of stress, or the packing of units, nature often defaults to hexagonal symmetry. It is a pattern of stability and efficiency written into the laws of physics and geometry. Saturn's hexagon is a member of this same family, just executed on a literally planetary scale. Instead of a thin layer of water on a stove, the fluid is Saturn's deep atmosphere, thousands of kilometers thick. The heat source is not a burner, but the planet's own fiery interior. The constraints are the planet's rapid rotation and the powerful Coriolis force. Yet the underlying equation is similar, a system seeking the most stable, energy-efficient way to organize chaos. When you understand that, the alien storm feels less like a supernatural sigil and more like a majestic signature, the universe applying a familiar rule with unimaginable power. It connects the simmering pot on your stove to the churning clouds of a gas giant, a reminder that the same elegant principles shape our world and those spinning in the distant dark. There is a moment in science when data transcends into art. The Cassini spacecraft gifted us such a moment with every high-resolution image of Saturn's North Pole. The hexagon is not merely a diagram of wind speeds, it is a cosmic fresco painted on a canvas of hydrogen and helium. Its 6 sides are etched with a ruler's precision, a boundary so sharp it seems drawn by an invisible hand. Yet, look within those golden walls. The backdrop is a turbulent sea of softer clouds, swirling in muted bands of cream and pale yellow, a constant churning chaos. The contrast is breathtaking, a perfect, fragile polygon suspended within a perpetual storm. At its heart, the deep blue vortex spins like a sapphire set in a geometric ring of ancient gold. This is not a computer simulation. It is a real place, a vast and silent arena where the laws of physics perform a ballet of unimaginable scale. The light of a distant sun, filtered through layers of hydrocarbon haze, gives the entire scene the warm, ethereal glow of a perpetual sunset on a world without a surface. It feels both impossibly alien and strangely familiar, like a symbol from a forgotten language written across the sky. This image speaks to something deeper than scientific curiosity. It captures the eternal dance between order and chaos, a theme that has captivated artists, philosophers, and mathematicians for millennia. In our own world, we see this tension in the spiral of a galaxy and the branching of a tree, in the predictable rhythm of tides and the unpredictable fury of a thunderstorm. Saturn's hexagon is this universal concept made manifest on a planetary stage. It is mathematical purity emerging from atmospheric anarchy, a stable idea born from relentless motion. To gaze upon it is to understand that the universe possesses an inherent artistry. Our drive to explore is not just a search for answers, it is a pursuit of beauty. We send robotic emissaries across the solar system, and they return with revelations that stir the soul as much as they challenge the intellect. The hexagon reminds us that some mysteries are not problems to be solved, but wonders to be contemplated. It asks us to pause in our analysis and simply marvel at the fact that such a thing exists at all, a perfect geometric dream spinning in the endless night. That artistic wonder is not locked away for scientists alone. You can join the search for understanding because the story of Saturn's hexagon is still being written, and new chapters often come from unexpected places. While spotting the hexagon itself requires a telescope far beyond most backyard setups, the broader field of planetary observation is rich with opportunities for anyone with curiosity. Amateur astronomers around the world regularly train their lenses on Saturn, capturing the tilt of its rings, the shifting of its cloud belts, and the dance of its moons. Organizations like the Association of Lunar and Planetary Observers serve as hubs where these dedicated skywatchers share images and reports, contributing to a long-term record of how gas giants change over time. A sharp-eyed observer might document an unusual storm in Saturn's mid-latitudes or a change in the hue of its bands, adding another piece to the global puzzle of its climate. This tradition of public contribution stretches back centuries, and today it is amplified by the Internet, connecting a global community that watches the sky. For those without a telescope, your computer can be a powerful instrument. Citizen science platforms invite the public to sift through the mountains of data sent back by spacecraft. Projects hosted on websites like Zooniverse have allowed volunteers to help classify cloud features on Jupiter or to mark dust devils on Mars. While a dedicated Saturn hexagon project may not always be active, the principles are the same, and new initiatives are constantly launching. You could be asked to trace atmospheric bands in old Voyager images to help train artificial intelligence, or to flag interesting structures in millions of infrared data points. This is not busy work, it is genuine research. The human eye and brain are exceptional at pattern recognition, often spotting anomalies or trends that algorithms might miss. By participating, you become part of the analysis team, helping professional scientists navigate an ocean of data to find the clues that might crack the hexagon's code or reveal another mystery entirely. The journey of discovery is also just a click away. Space agencies like NASA and the European Space Agency make their mission updates, raw images, and scientific findings freely available to everyone. You can follow the official social media accounts for ongoing missions like the James Webb Space Telescope, which may one day turn its infrared gaze toward Saturn's deep heat signatures. You can browse the vast public archives of the Cassini mission, where every stunning image of the hexagon is stored and waiting to be explored. By following these channels, you become a vicarious member of the mission control team, sharing in the excitement of new data and the suspense of a spacecraft's final plunge. This open access transforms space science from a distant academic field into a shared human experience, a story unfolding in real time that we can all watch together. That sense of shared endeavor is perhaps the most important legacy of a mystery like the Hexagon. It reminds us that the cosmos does not belong to any single nation or institution. It is a common frontier. When a spacecraft beams back a picture of a six-sided storm, that image belongs to a curious child in Mumbai, a retired teacher in Buenos Aires, and a programmer in Oslo just as much as it does to the engineers who built the probe. Every question asked by a viewer, every sketch made by an amateur astronomer, and every classification clicked by an online volunteer adds to the collective effort to understand our place in the universe. The Hexagon is more than a storm, it is an invitation. It invites us to look up, to wonder, and to participate in the grand and collaborative project of discovery. Our robotic eyes at Saturn may be closed for now, but the conversation they started continues here on Earth, in labs, in online forums, and in the minds of everyone who sees that impossible shape and thinks, what does it mean and how can I help find out? The perfect geometry of Saturn's hexagon is a siren call for speculation. It looks so deliberately crafted that a persistent myth has taken root, the idea that this is not a storm at all, but an alien megastructure. Perhaps it's a colossal energy grid, a docking station for spacecraft, or even a stargate. This is a compelling story, but it is a story, not science. Let's be clear, there is zero evidence of any artificial origin. The hexagon is a breathtaking demonstration of physics, not engineering. Think of a snowflake. Under a microscope, its intricate six-sided symmetry seems impossibly designed, yet we know it forms naturally from the crystallization of water under specific conditions. The hexagon is a snowflake writ large, a pattern emerging from the complex crystallization of wind, rotation, and heat. Its geometry is not a blueprint, it's a signature, the mathematical result of a fast-spinning fluid finding its most stable state. To claim it is artificial is to misunderstand the profound creativity of natural laws, which can sculpt order from chaos on scales far beyond human capability. Another common misconception is that the hexagon is a solid object, a giant honeycomb structure embedded in Saturn's clouds. This is not the case. You cannot land on it or touch its walls. What we are seeing is a pattern of motion, a river of air. It is a jet stream, a boundary where winds of different speeds meet and create a standing wave. If you could float within it, you would experience a hurricane-force wind whipping you along a six-sided racetrack, but you would pass right through the walls because they are not walls at all, just a transition zone between two atmospheric bands. The sharp edge we see in images is an illusion of contrast, like the clear boundary between a fast-moving river and the still water near its bank. This distinction is crucial. It transforms the hexagon from a static monument into a dynamic process, a dance of forces rather than a fixed thing. Some wonder if the hexagon is a new phenomenon, a sign that Saturn is undergoing some dramatic change. The truth is far more impressive. We have confirmed its existence for over 40 Earth years, and it shows no signs of fading. Given its incredible stability, it is almost certainly centuries old, possibly even millennia. It is not a symptom of change, it is a testament to constancy, a permanent feature of Saturn's climate. This longevity actually argues against any fleeting or artificial cause. A manufactured object would degrade, a temporary atmospheric glitch would have dissolved. The hexagon's endurance points to a deep, fundamental, and self-sustaining natural process within the planet. It is as much a part of Saturn as its rings, a fixture of its alien weather that operates on timescales that humble our human perspective. Dispelling these myths is not about shutting down imagination, it's about redirecting wonder to where it truly belongs. The reality is more astonishing than any fiction. We do not need to invent alien architects when the laws of fluid dynamics can sculpt a perfect hexagon 25,000 kilometers wide. We do not need to imagine solid walls when the invisible force of a jet stream can carve a shape into the sky for centuries. By letting go of the easier, sensational explanations, we open ourselves to a deeper and more rewarding mystery. We get to ask how, not who. We get to marvel at a universe where mathematics becomes visible, where the simple act of a planet spinning and churning can write geometry across the clouds. This is the heart of scientific literacy, trading the comfort of a simple answer for the profound thrill of a real, complex, and beautiful truth. The hexagon is not evidence of others out there. It is evidence of the incredible things nature can do all on its own. From a blurry anomaly in Voyager's data to a majestic, living system in Cassini's gaze, the hexagon has defined a generation of planetary exploration. We have measured its staggering size, watched its colors shift with the seasons, and modeled the fluid dynamics that can carve such a shape from pure chaos. We now see it not as a static painting, but as a resonant wave, a planetary-scale engine fueled by Saturn's inner fire and sculpted by its furious spin. Yet for all we have learned, the hexagon remains at its heart an enduring enigma. We still debate the true depth of its roots and the precise cosmic tuning fork that sets its six-sided frequency. This perfect geometric storm is a humbling reminder. It tells us that even in our own solar system, on a world we have visited with our robots, profound and beautiful mysteries still spin in plain sight. It is a testament not to what we know, but to how much wonder is left to uncover. So the next time you see Saturn as a bright, steady point of light in the night sky, remember. At its north pole, hidden from our earthly view, a continent of wind traces an ancient, six-sided path. It is a puzzle written on the clouds, a silent question from a giant world, inviting us to keep looking, keep questioning, and never stop marveling at the strange and geometric music of the cosmos.